Hello everyone, this is Reza Vaezi and you are going to learn about the basics of linear regression analysis through this short lecture recording. What you have learned so far in this series of lectures and so far in class, they all was under the exploratory analysis or descriptive analysis. From now on, we switch to predictive analysis. This diagram, which you've already seen in previous lectures, tells you about different branches of data mining. So there is one big branch of exploratory or explanatory analysis, which most of unsupervised data mining methods will fall under that category. The most famous ones are clustering and association rules analysis that you've already learned about. From now on, we are going to focus on predictive analytics, which most of them are supervised methods or supervised methods of data mining. The difference between unsupervised methods and supervised methods is that supervised methods have a target variable. They have a target variable or a label variable that you want to predict. So it's not all about describing data. From now on, you will focus on predicting how a variable would behave or what values a variable will take according to some other variables in your dataset. And generally, you can categorize predictive and supervised data mining methods into the regression-based methods and classification-based methods. Today you are going to learn about the most basic regression-based method, which is called linear regression. Linear regression is one of the most commonly used predictive analytics techniques for non-categorical or continuous numeric targets. It assumes that there is a linear relationship among your target variable or dependent variable and your set of independent variables. Remember, in linear regression, the target variable is also called dependent variable. If you go to the classic text for linear regression, you will not see target variable, but you will see dependent variable. It means a variable that its value is depending on some other variables. Those variables that contribute to the dependent variable value are called independent variables. Linear regression finds the best fit line that summarizes the sum of a squared of vertical distances from the data points to the line. You may wonder what this means. You will see it in the next slide what this actually means. As I said, linear regression assumes that there is a relationship between your independent variables and your dependent variable. Here is the most basic and the simplest form of linear regression, which we only have one independent variable, and that is x. Your dependent variable or target variable here is y. You can see that there is an apparent relationship between x and y. As x increases, y also increases somehow. In linear regression, you want to estimate or predict the values of y when you are given values of x. That's the whole purpose of linear regression. And for that prediction, you want to come up with an equation that refers to this blue line that you see in this slide. The blue line is an estimate of y. You can give the value of x to that equation and will give you the y values. And the mathematical process involved in estimating this line always try to minimize the squared distance between these dots and the center of the line, between your data point and the center of the line. The smaller the sum of these distances, the better the estimation, or the better the line. The line is more representative of what actually is going on in the real world. So in linear regression, you want to estimate that line. And remember, in majority of cases, in most cases, you will have more than one independent variable. And once you have more than one independent variable, it's not easy to plot the linear regression line. Maybe you can still do it when you have two variables, two independent variables. You can do a 3D plot, but more than that, we'll get into dimensions, fourth dimension, fifth dimension, and will get into multidimensional spaces that our brain is not equipped to understand. But in reality, you usually have more than two or three independent variables to be used in estimating your dependent variable or in predicting your dependent variable. So once again, linear regression assumes that there is a linear relationship between your dependent variable and your independent variables. In the simplest form, we are trying to come up with this equation: y equal to a plus bx. Y is your dependent variable, a is your intercept, b is your slope, and x is your independent variable. In more complex form, you will have your dependent variable y is equal to a, which is the intercept, plus the slope of x1 multiplied by x1 plus the slope of x2 multiplied by x2 until your last variable. The line in linear regression typically represent the average or the center of all the points in your dataset. And for linear regression, you have to keep this in mind that both your dependent and all of your independent variables, they have to be of numeric type and of continuous type. It is especially important to make sure that your dependent or target variable is of continuous type, not of a discrete type or categorical. By continuous, you have to be able to think that your dependent variable can assume any value within a range. By discrete or categorical, your dependent variable or your target variable can only assume certain values. For example, when you are asking about customer satisfaction and you have satisfied, then you have them answer you either they're satisfied, not satisfied, or neither. You're dealing with categories. But if you give them a scale that they can, for example, choose from -1 to +1, -1 representing your dissatisfied, 1 representing your satisfied, but they can choose anywhere in this scale. They can choose 0.07, they can choose 0.4, they can choose 1. If you do it as a scale, it'll be continuous. If you don't do it as a scale, if you do it as categories, it'll be discrete or categorical. For linear regression, you have to make sure that your dependent variable as well as your independent variables, they are all numerical and of continuous type. Sometimes you can use dummy variables to change your categorical independent variables to continuous or numerical variables, but that is not recommended, and you have to know more about the regression process, and you have to know more about the statistical underlying of regression equation to be able to do that correctly. Before you can decide and apply linear regression to a problem, there are some assumptions that you need to be aware of. It starts with this assumption that there is a linear relationship between your target variable and your independent variables. It means that you can draw a straight line to represent the relationship between your x's and your y. Also, it assumes that the target variable is of numerical and continuous type. The assumption holds true for independent variables, but it is not as strict as when it applies to your dependent or your target variable. Yet still, all variables have to be of numerical type without question. The next assumption is that all your variables follow a normal distribution. And you have to note that your independent variables, the ones that are predicting your target variable, are not highly correlated. Otherwise, you run into a problem known as multicollinearity. And the last assumption is the homoscedasticity assumption, which assumes the variance around the regression line is the same for all values of predictive variable x or the independent variable x. It means that you will have similar variance or similar distribution of points above and below the line, around the line, if you plot it. Now, in reality, it's difficult to find a data set that exactly comply with all these assumptions. Any data set that you deal with will somehow have issues with one or more of these assumptions. How to deal with assumptions, what corrections to use, is beyond the scope of this course. Regression is such a huge and deep subject that you can find a course only on regression on stat department at both undergraduate and graduate and even PhD level. It's a huge subject. How to deal with the violations of these assumptions is again beyond the scope of this course. But you need to know about these assumptions, and you need to know when these assumptions are severely violated, your regression results may not hold true, and you need to perform some mediations, some corrections into your linear regression model. There is this important consideration when applying linear regression analysis to business problems. Linear regression analysis is really good at finding global effects or global patterns in your data as opposed to local effects. It is essentially incapable of revealing any sort of localities in your data. And what do I mean by that? Let me give you an example. You all know that the risk of being involved in a car accident decreases by age. That's why when you are younger, you have to pay higher premiums for your car insurance. And as you get older, the premium decreases. So regression is capable of finding this global effect, that the risk of driving or the risk of getting involved in an accident will decrease with age. But that is not always correct. At some point in your age, again, the risk of getting involved in an accident increases. Regression is incapable of finding that. You know that older people above 65, they start becoming more dangerous. They start being involved in more accidents. So not always as you age, your risk decreases. At some point, it starts increasing again. To figure these effects out, to find these effects out, you have to be equipped with excellent business knowledge. You need to know your business inside and out, and you need to be aware of these localities. Usually, if you don't know it, somebody who has been in that industry for a while should know about these localities. When you have local effects, in order to detect them using regression, you need to divide them into local groups. So in the example of car insurance, you need to have one group for people from 18 to 65 and then run a regression analysis for them, and then you will need another group of customers from 65 and above and run a different regression analysis for those customers, because these equations, these regression analysis will be different for these groups of customers, or for these two groups of customers, because they behave differently. Another example of global effect versus local effect is a newspaper subscription, like the newspaper print subscription. There is this global effect that as you move away from the city center, the subscription rate falls, but that does not hold true. Yes, as you move from downtown, from where all the offices are located and you have all those companies and offices subscribing to your paper, the subscription rate starts falling. But somewhere in the suburbs, where you get to wealthy suburbs, when you have wealthy neighborhoods, then again in those suburbs the subscription rate will start increasing. And after you are past those suburbs, then the subscription rate starts decreasing again. So globally, a regression analysis will tell you that with distance, the subscription rate for your newspaper will fall. But you need to be aware of these local effects. And when you are aware of these local effects, then you will need different regression equations and regression analysis to detect each of these localities. So again, regression is not good for finding local patterns, only global and general patterns.